Question 8. A Cobra III spaceship passes a stationary asteroid at 93% of the speed of light. If the ship's rest mass is 100 tons, find its mass relative to a Hermit living on the asteroid. So what do we use here? Well, of course we use what we've just learned, mass dilation. So, here's our equation for mass dilation. The relativistic mass of an object is increased by this factor. This is a factor that's always going to be less than 1, and if we divide by a number that's less than 1, we end up with a bigger number. So, V over C is going to be 0.93, as we can see. We'll square that number, and so substituting it in, we end up with this expression. 100 tons over the square root of 1 minus 0.93 squared. Now hang on here, you ask, where did the C go? Well, it's quite simple really. We had defined V as a multiple of C, right? So V is given by 0.93 C, and we can see that over here we're dividing that whole thing by C and then squaring it. The C's just cancel out. And so we end up with just this simple number without units that we can square. Alright, so we can use a calculator to evaluate that answer, and we'll end up at 272 tons, which means that the spaceship, when it's moving at 93% of the speed of light, is almost 3 times heavier than in its rest frame. Part B. If the rock Hermit measures that the Cobra's length is about 24 meters, find its proper length. So if the proportion that we worked on before was anything to go by, then it will be a little bit less than 3 times as long in its rest frame, right? So given that 3 times 24 is 72, we're expecting an answer that's a bit less than 72. So let's use our equations. Now we know that length contraction is given by this equation. Relativistic length equals rest length times this factor, which is less than 1. This means that relativistic length will be shorter, right? But we're already given relativistic length. What we want to find is its proper length, that is, the length when it's at rest, L0, right? So we need to rearrange this equation a bit. There we go. Now it looks just like the equation for the last question. Once we substitute in V, we will of course have exactly the same denominator for the fraction. So our equation looks something like this, and simplifying we end up with 65.0 meters, which, just as we expected, is a little bit less than 3 times as long. Part C. The pilot of the Cobra waves hello to the Hermit on the asteroid. This action takes 2 seconds in the ship's rest frame. How long does it take in the Hermit's rest frame? So now, according to the Hermit, the pilot, we'll call him Commander Jameson, is moving at 93% of the speed of light, and he performs an event that takes 2 seconds in his own frame, but will take a longer time when he's moving, right? But that's because time inside this moving frame of reference is going to slow down. So there's our T0, we're looking for TV. There's our equation relating the two. Once again, we have a similar factor on the bottom, and we know that the factor will be a little bit less than 3 times as long. So we're expecting the action to take a little bit less than 6 seconds. Substituting in our numbers, we end up with 5.44 seconds, which is pretty close to the estimate that we gave.